What if a coin landed on both heads and tails when it hit the ground? This isn't magic. It's the quantum revolution just honored by the 2025 Nobel Prize in Physics. For a century, quantum physics has baffled us. It explains how electrons tunnel through walls and particles exist in two states at once, but only in the microscopic world. Macroscopic objects, a ball thrown at a wall always bounces back. This divide became physics' greatest paradox until three men destroyed it. On October 7, 2025, the Nobel Committee awarded John Clark, UK, UC Berkeley, Michel Deverett, France, Yale, and John Martinis, US, UC Santa Barbara for proving quantum weirdness isn't just for atoms, their tool. A tiny circuit you could hold in your palm. The key lay in superconductivity materials that conduct electricity with zero resistance at ultra-low temperatures. Here, electrons abandon their individuality to form Cooper pairs, acting as a single quantum entity. Think of a crowd turning into a synchronized dance troupe. In 1984, the trio built a circuit where Cooper pairs were trapped, current flowed, but no voltage existed. It was like a ball stuck in a valley with no way out. Classical physics said it would stay there forever. Quantum physics begged to differ. For weeks, they cooled their device to near absolute zero, eliminating thermal noise that would drown quantum signals. Then it happened. The oscilloscope needle spiked. Voltage appeared out of nowhere. The Cooper pairs had tunneled through the insulator as a group. This wasn't just a trick of individual particles. Thousands of Cooper pairs acted as one, defying classical barriers. It was the first time humanity observed quantum tunneling in a macroscopic system, a physical object large enough to measure directly. Theoretical physicist Anthony Leggett called it Schrödinger's cat made real. Unlike the famous thought experiment, this cat was a circuit, a tangible system existing in quantum superposition. The rules of the tiny now governed the large. To confirm, they bombarded the circuit with microwaves. Quantum theory predicts systems only absorb energy in discrete packets, and that's exactly what they saw. At 5.2 GHz, the tunneling rate skyrocketed. The circuit was quantized, just like an atom. Quantum tunneling is random, so they repeated the experiment 10,000 times. The data formed a perfect curve matching quantum predictions. The longer the circuit stayed in zero-voltage state, the higher its energy level. Chance had become certainty. We turned a theoretical curiosity into an instrument, Deverett later said. Their Josephson junction was more than a lab toy. It was the first artificial atom with wires and interfaces. This discovery didn't stay in academia. Martinis later used these circuits to build quantum bits, the core of Google's 2019 quantum supremacy experiment. Today, IBM, Google, and Alibaba rely on this exact technology for their quantum computers. The implications stretch further. China's 2025 micro-nano quantum satellite uses related tech for unhackable communication across 10,000 kilometers. Quantum sensors built on these principles can detect underground minerals or diagnose diseases earlier than ever. Clark's team now hunts for axions, hypothetical dark matter particles. His squid detectors, descendants of that 1980s circuit, are sensitive enough to measure magnetic fields 1 trillion times weaker than Earth's. A century after quantum mechanics was born, we've finally broken the wall between micro and macro. The 2025 Nobel laureates didn't just explain nature, they gave us the keys to rewrite technology.